Hello, so in this video I'm going to be giving a quick run through of atomic structure. So, as we know it now, atoms are made up of protons, electrons and neutrons. There's some shortcut symbols that we use quite a lot in chemistry. P with a superscript of a plus sign represents a proton, E with a negative sign over it represents an electron, N superscript 0 represents a neutron. So the protons and neutrons exist in the nucleus, and then the electrons exist in what we call orbitals, but another general name for that would be the electron cloud. So you can imagine that the nucleus is a really, really tiny dot in the middle of this circle, and the rest of the circle is all the where the electrons are. If you imagine a propeller spinning around, you don't see the individual blades, but you know generally the area that they take up. Same sort of idea with electrons. They take up this area. There's an attraction between the negative electrons and the protons, so they don't fly away completely. So they take up this area. They're moving really quickly with lots of energy, or varying amounts of energy depending on how close they are to the nucleus. And so the big idea here is that the nucleus is so small in the middle. So it's basically about 1/100,000th of the rest of the atom. So almost impossible to draw it to scale like this, but if you imagine putting a peanut or M&M in the middle of CenturyLink field, that would represent the nucleus. The rest of the stadium would represent the rest of the atom. So a huge difference between the size of the nucleus and the size of the atom. Also now we know that these three subatomic particles are made up of quarks. Quarks will actually be very important when we talk about how protons and neutrons exist in the nucleus, and how that there's a force that keeps those together. But just to give you a general size of the atom, or of atoms, obviously different atoms have slightly different sizes depending on how many electrons and how many protons they have. This number represents kind of the general ballpark figure of an atom, and it's called about 10 nanometers, which is really, really small. And so I'm going to erase this really quick and move to my next little topic. So just the big idea is that atoms are really, really small, and the nucleus is even smaller. So on the periodic table, it's a really nice summary of a lot of information. If you know how to uncover that information, it can save you a lot of time and energy. So let's say that this is an element, it's called element X. On most periodic tables, you see this notation. The A stands for mass number, and the Z would stand for atomic number. So the mass of an atom is basically the the protons and the neutrons. They are a few thousand times heavier than electrons, and actually when we talk about the mass of electrons contributing to the mass of the atom, it's negligible. It's so small compared to the mass of these two. So we really only worry about the neutrons and the protons and their masses. So the mass number represents the mass of the protons added to the mass of the neutrons. You can have different elements with the same mass number, and I'll talk about that in a moment. That's the idea of isotopes. But you can only have, for a stable atom, you can only have one number of electrons and protons for that, and that represents that particular element. So the number of electrons and protons is equal in atoms, and then it's unique to that element. So the atomic number we represent as a Z, and the mass number is A. So the atomic number represents the number of electrons and the number of protons. So say for example if the atomic number was 5, that would represent 5 electrons and 5 protons. So the mass number represents the number of protons added to the number of neutrons. So if we go with this example of 5, an atomic number of 5, that means there's 5 protons. And then the number of neutrons is added to that to get the mass number. So if you need to know the number of neutrons, in an element, you take the mass number, so that would be A, and you subtract Z. So this difference would give you the number of neutrons. All you have to do to figure out the number of electrons and protons, though, is just look at the atomic number. So, for example, if it's 25 electrons, 25 protons. The number of neutrons, though, you have to do this little sum, or this little problem. So that's how you figure out the number of electrons, protons, and neutrons. So you're probably wondering, how is it that if you have a nucleus that just contains protons and neutrons, how do they stay together? And well, the answer is something called a strong force. So the idea is, the fact is, there's four main forces of nature. Gravity is one, electrostatic force, the attraction between negative and positive. The electrostatic force is basically what helps keep the overall atom together. The attraction between negative electrons and positive protons. So the electrostatic force keeps the overall atom together. The strong force helps keep the nucleus together. It's a longer story than we will actually get to right now, but it involves these particles that make up these three particles, mainly the protons and neutrons. And the name of the quark that's involved is called a meson. And basically, one particle splits into even more particles, and it's the interaction between those two opposite particles that help keep the protons all in one nucleus. And you can think of the neutrons as kind of like the glue that helps keep the nucleus together. But there is a theory, it involves these quarks. And it's a really important idea, especially in astronomy, because this is the idea of this will help stars form and also stay together. So understanding this idea, the quarks separating and then joining back together and helping keep the nucleus together is helping us understand a lot of astronomy, and especially with our own planet, with the solar system and the sun. So really important idea, and that's how it's used. But the name of the force keeping the nucleus together is called the strong force. Other big important force would be electrostatics force. Opposites attract, positive attracts negative, and then like charges would repel, so positive would repel each other. Just check my little cheat sheet. Okay, so I'll erase this really quick, and then we'll talk about isotopes. I'll keep this up there. So, in chemistry, we understanding the idea of isotopes is really important. Carbon dating helps tell you if something was alive. So if it has organic material, if it was alive, then you can date back how old it is. There's a limit to carbon dating, but there are other methods. So radioactive carbon is an isotope of regular carbon, and regular carbon makes up coal, pencil lead, that sort of thing, graphite. Also, there's a version of oxygen that's used in glucose, and that's used in medical diagnoses. So radioactive isotopes are used quite a lot. Some of them are radioactive, and that allows you to use them and trace them in certain ways. But the idea of an isotope is, let's say for example we use carbon, and we use this notation. So the atomic number was down below. So carbon has an atomic number of 6. And then one of the versions of carbon has an atomic mass, or a mass number of 12, which represents 6 protons plus 6 neutrons. Added together, and this represents 6 electrons. 666, number of the beast. So protons plus neutrons is up here, and then this represents the number of electrons, the atomic number, and protons actually, because they're always equal in an atom. So then the isotope of carbon that's frequently used in carbon dating is this version. It's got 1 extra neutron. So this would actually have 6 protons, 6 electrons, but 7 neutrons. So that we call these isotopes. same number of electrons, same number of protons, but different or varying numbers of neutrons. So, and again, the idea of isotopes will actually come up a lot in nuclear chemistry. And they do have very specific uses, medical, geological, so very important. So, that's it.